Dear classmates, welcome back to the test compression chapter. In the previous video, we talked about software techniques. However, we need more than 1000 times of compression ratio in the future. Software techniques alone is not good enough to achieve such a high compression ratio. So, in this video, we are going to talk about hardware techniques. We will focus on test stimulus compression in this video. In the next video, we will then talk about test response compression techniques. Remember, in chapter 14, we show some real BIST data. This slide compares a traditional ATPG test solution with a built-in self-test solution. Apparently, built-in self-test require very low test data volume. However, the BIST fault coverage is not as good as ATPG fault coverage, and the BIST does not always save test time. This slide compares three compression techniques. On the left extreme, we have the pure BIST solution. The advantages are low-cost ATE and zero test data volume. However, BIST fault coverage is low, and we don't save test time. On the right extreme, we have the traditional ATPG and ATE solution, where we require very expensive ATE and the test data volume is very large. But the advantage is fault coverage is very good. Unfortunately, we cannot save test time. So now we have a solution in the middle where we have on-chip DFT for hardware test compression. This solution has all the advantages, including low-cost ATE, small test data volume, high fault coverage, and also it can reduce our test time. So, hardware test compression has advantage of both BIST and traditional ATE technique. So it is now a very popular technique in modern IC design. Traditionally, we need a very large ATE to apply very large volume of test data using many test channels. And we also collect the CUT response back to the ATE. The number n is very large, so the communication between ATE and the CUT is very expensive. Now, with test compression DFT, we can use a very simple small ATE which stores a very small amount of test pattern, and we send this data to the chip. On the chip, we have a decompression circuit that decompresses this small amount of data into a large amount of original test data. On the output side, we have an on-chip compressor which compresses the CUT response and send it back to the ATE. Because M is much smaller than N, so we can save a lot of cost in ATE and CUT communication. Now we will introduce three types of hardware test stimulus compression in this video. The first one is code-based scheme, and the second one is linear compressor-based scheme, and the third one is broadcast scan-based scheme. Under the code-based scheme, we will introduce dictionary code and Huffman code, which were invented in 2002 and 2003 respectively. The idea of dictionary code compression is we can translate a symbol into a code word Typically, the number of bits in the code word is much smaller than the number of bits in a symbol. For example, for this simple dictionary, the number of bits in the code word is 2, and the number of bits in the symbol is 4. So we use 2 bits to represent the data of 4 bits. In this way, we can achieve data compression. As is shown in figure 6.3 in our textbook. Suppose we have B bits coming from the tester. After the dictionary, we will translate this into a scan slice of N bits, where a scan slice means a vertical column of scan chain input. The compression ratio of this technique is equal to N over B, which is the original data divided by compressed data. For example, if we apply this technique, then N is 4, B is 2, so the compression ratio is 2. The dictionary code compression is called fix-to-fix compression technique because the original data is coming at the fixed rate and the compressed data is coming out at the fixed rate. The dictionary code compression cannot provide a very good compression ratio, so we can further move on to the Huffman code compression, which is a fixed to variable rate compression. The idea of Huffman compression is that we count the frequency of occurrence of each symbol, and we assign higher frequency symbol to shorter code word. In this way, we can compress the data in a more efficient way. This is an example shown in textbook table 6.2. Suppose the frequency of occurrence is totally 60, and the pattern 0010 appears 22 times. So we assign it into a small Huffman code of 2 bits only. On the other hand, the pattern 0011 appears only 1 time. So we assign a very long Huffman code with 6 bits. And the result is shown here. We can see that in this figure, Huffman code effectively compressed the original data. So how can we obtain the Huffman code? We can use a greedy algorithm to construct a Huffman tree. The idea is that we can merge 2 lowest frequency symbols as one node. For example, S11 and S12, they are 2 lowest frequency symbols, so they are merged into one node. In this tree, the numbers in the node represent the frequency of occurrence. Similarly, S9 and S10 are merged into one node, and these 2 nodes are merged into a bigger node of total frequency of occurrence of 4. We can gradually construct this tree from the bottom up. On the top of the root, we have a total frequency of appearance, which is 60. On the right hand side, we show the pseudocode of Huffman compression. If you want to know more detail, please see the textbook. It has been proven that the Huffman code is optimum prefix code. Now, it's time for you to work on a quiz. Given this Huffman code, where the pattern 000 appears 6 times, and the pattern 1010 appears only 1 time, please calculate the compression ratio of this Huffman code. Now please pause the video and do the calculation. Okay, have you done yet? The compression ratio is like this. In the numerator, it's 4 bits by the total frequency of appearance of 10. In the denominator, we have 1 bit that appears 6 times, and the 2 bits that appear 3 times, and 2 bits appear 1 time. So the compressed data is 14 bits, and the original data is 40 bits. So the compression ratio is almost 2.9, which is better than the previous dictionary-based technique. So in summary, we introduced the code-based compression schemes, but this scheme has many problems. First of all, the dictionary technique requires a very large area overhead to store the dictionary, which is not a very good solution. The Huffman technique requires synchronization among ATE and the CUT. Typically, ATE sends data at fixed rate, but the Huffman technique requires variable rate. This is a problem because we don't know how many bits we want to send to the CUT at a time. So this technique is not easy to implement practically. In conclusion, code-based techniques are not very useful in practice. The next one is broadcast-based schemes. Broadcast scan was first proposed by Professor Lee in 1998. The idea is very simple. Since there are many compatible test patterns, why don't we just broadcast them together? For example, for these 2 combinational circuits, circuit C1 needs test pattern 1 don't care 0, and the circuit C2 needs don't care 1. These 2 test patterns are actually compatible, so we can tie them together in test mode and apply one pattern 1110. In this way, we can test both 2 circuits. Similarly, for sequential circuits, suppose 3 circuits require the same compatible test pattern. We can tie their scan input together and broadcast this test pattern 1110 to these 3 circuits. And then University of Illinois also proposed a similar idea called Illinois scan. They divide the scan chain into segments and they tie this input together in broadcast mode. We first apply compatible test patterns in broadcast mode. In this way, we can compress the test data and reduce the test time. If we have incompatible test patterns, we can apply them in serial mode. In this way, we can apply any pattern to maintain our fault coverage without any degradation. And Dr. Wang also proposed a similar idea called virtual scan in a commercial tool. The virtual scan has a Procaster, which consists of some simple gates such as exclusive OR, inverter, NAND, NOR, etc. When we run the ATPG, the Procaster is treated as part of the CUT, so we generate test patterns for CUT and the Procaster together. There are three advantages of doing this. First, we don't need to solve any linear equation. Second, we can use dynamic test compression to effectively reduce the test pattern count. And third, according to Dr. Wang's experiment, the fault coverage loss is very little. Now it's time for you to work on this quiz. Consider this Illinois scan. Suppose 95% of test patterns can be applied in the broadcast mode, and the remaining 5% has to be applied in serial mode. Please calculate the compression ratio for this Illinois scan. Now please pause the video and work on this quiz. Okay, are you ready for the answer? So, suppose the original data volume is 4. If we apply the broadcast mode for 95% of the test pattern and the serial mode for the remaining 5%, then the compression ratio is almost 3.48. Have you got it correctly? So the broadcast scan looks like a very smart idea. But there is one problem. How can we broadcast those incompatible test patterns? For example, in this case, channel 2 and channel 6 are compatible in some test patterns, but unfortunately, they are incompatible for some other test patterns. For example, due to the conflict in the middle, scan chain 2 and the scan chain 6 are incompatible. So now, if we want to broadcast test pattern to scan chain 2 and the 6, then we have some conflict. What can we do? We can have a reconfigurable Procaster. So we add some mux to control the Procaster. Suppose the control input is 0. We broadcast input pin number 1 to scan chain 2, 3, and 6. If we change the control bit to 1, in this way we separate the scan chain 2 and the scan chain 6 so that we can control them in a different way. By using the reconfigurable Procaster, we can now broadcast incompatible test patterns in different configurations. Now we move on to the last technique, linear decompression based scheme. If you remember, in the BIS chapter, we introduced a technique called LFSR Receiving. In this technique, we load LFSR seed, run C cycles, and we change an LFSR seed and run another C cycle, and etc. For example, given this LFSR, suppose we want 3 test patterns, 1000, 1100, and 1101. Instead of letting the LFSR running freely for 9 cycles, we can try to reseed to save test time. We load an initial seed, apply the test for 2 cycles, and then we reset to 1101, and we apply the test for another 2 cycles. So totally we only need 4 cycles. If we use LFSR Receiving, we can achieve the same fault coverage, but the test length is much shorter. It turns out that LFSR Receiving is also very useful for test pattern compression. Suppose that we have an n degree LFSR that feeds a scan chain of 1000 scan cells. We assume only 5% of the bits are carrier bits. If you remember, in chapter 13.4, we mentioned that the number of LFSR degree is equal to the number of carrier bits plus 20. So according to these numbers, we need a 70 degree LFSR. Let's apply 10 patterns between receiving. So the compression ratio would be the original data volume divided by the LFSR seed, which is 1000 times 10 divided by 70. So we have 143 compression ratio. This is a very, very large number. So receiving is actually very good for compression. But if we rely on receiving, the fault coverage is still the same as the original LFSR. So how can we improve the fault coverage? We can use LFSR with external input to improve the fault coverage, such as the ring generator. A ring generator is very similar to an LFSR, except that now we have extra multiple inputs. For example, this figure shows an example ring generator with 2 external inputs that feed 4 scan chains. So in this way, the compression ratio is 4 divided by 2, which is 2. We can run the ATPG on the CUT to obtain a test pattern of 12 specified bits that correspond to 12 linear equations in the linear system. For the ring generator, we have 10 variables for the 12 equations, including 4 initial seeds in the LFSR. Also, we have 6 external inputs. So, in conclusion, the ring generator introduced more free variables, so the probability of solving the linear equation system is higher, so the fault coverage can be improved. Solving ring generator input is very similar to solving LFSR seed. We solve linear equation system AX equal to Z, where A is a matrix with R rows and C columns, and X is a vector of free variables. Z is a vector of our desired test patterns. We can use algorithms such as Gauss-Jordan elimination to solve for the answer. The complexity of Gauss-Jordan elimination algorithm is OCR squared, which can be solved in polynomial time. The picture shows 2 examples of solving a linear equation system using Gauss-Jordan elimination. Sometimes we are lucky, we can find a solution successfully. But sometimes we are not so lucky. We cannot find the solution. So what can we do if we find no solution to the ring generator? We have several remedies. First, we can bypass the decompressor. We directly apply the test pattern. This would increase the data volume. The second remedy is that we can rerun ADPG. We change our test pattern. This would increase our runtime. The third remedy is that we can redesign our linear decompressor. We increase the number of free variables. And the last solution is a phase shifter. We can inject a phase shifter between the ring generator and our CUT so that we can shift the phase of the output. For more details, you can see chapter 14.5. Now, it's time for you to work on a quiz. Given this ring generator with 5 inputs and 100 output, what is the compression ratio? Please pause the video and work on this quiz. Okay, have you got it? Answer is easy. Compression ratio is equal to 100 divided by 5, which is 20. In summary, in this video, we introduce several hardware test stimulus compression techniques. The first technique is code-based scheme, including dictionary code and the Huffman code. Unfortunately, they are not very useful in practice. The second technique is broadcast-based schemes. They are very simple and effective. However, it's hard to handle incompatible test patterns. The last one is linear compressor-based scheme. They provide very good compression ratio, and in fact, it is the most widely used technique in modern IC. Before we end this video, we have one interesting FFT for you. We already know that ring generator has very good compression ratio. So, can we use it to reduce test time? Please think about it.